Hey fam, it's your boy, Mr. Wishart, coming at you with another hot video. This one is about scientific notation and operations with scientific notation. I got some slides to kind of like set the stage for this. First one right here, why do we need to do all this shifting of left and right, changing exponents? This is dumb, Mr. Wishart. So I've got this problem right here. Two numbers in scientific notation. First, we're going to add them in standard form, and then we'll add them in scientific notation. Let me make sure that I have a pencil for this, so give me just a moment. Okay. Sorry, should have written that out. 6.5 times 10 to the 8th. Plus 4.3 times 10 to the 5th. Cool.
Attention, all staff and students, the school is now unsecure. Get inside, lock outside doors until further notice.
Okay, well, there you go.
Attention, all staff and students, the school is now unsecure. Get inside, lock outside doors until further notice.
So first thing we're going to do...
Attention, all staff and students, the school is now unsecure. Get inside, lock outside doors until further notice.
First thing we're going to do is add these in standard form. So standard form is when you write out the entire number without using scientific notation. So we're going to have this 6 and this 5. And then since the decimal's right here, we're going to basically have 8 digits to the right of that decimal that we kind of need to add in here. So we've already got this 5, so then it's going to be 7 zeros. 1, 2, 3, 4, 5, 6, 7. So this becomes 650 million. Now I'm going to write this here, this 4.3 times 10 to the 5th. And so you're going to see why I'm writing this in pencil in a moment. Okay, so this 4.3 to the 5th becomes 430,000. And now if I add them, you know, we get zeros, 1, 2, 3, 1, 2, 3, add that, becomes 8, and that becomes 10. So when we add these together, we get like 1,080 million. However, I have screwed up. I have done something incorrect, right? Rather than lining my ones place up with my ones place, I actually line my one place up with my thousandths place, right? And that right there, that thousandths place, that's actually 3 differences in our exponents right there, right? So that's what I should be doing is lining it up on the right side rather than on the left side. So this becomes interesting, hold on, getting a phone call. Okay, so now I'm going to add them up. 0, 0, 0, 0, 3, 4, and then 650 million. So it's 650,430,000. That is actually much more reasonable to kind of deal with that. Now, one thing that you should realize that these numbers are technically also being multiplied by 10 to the power of 0, because 10 to the power of 0 is just 1, right? Now what we did here is we changed this exponent of 8 to 0. We subtracted 8 from it. So as our exponent went down, our decimal moved to the right, from here all the way to here, right? And similarly, when this exponent went from 5 to 0 by going down, we shifted our decimal from right here at that 4.3 all the way to the end right there. Okay, so if you're kind of like summarizing how to actually do this logically, you could say when your exponent is going down, you're shifting your decimal to the right. And then conversely, if your exponent was to go up, you would be shifting your decimal to the left when you're kind of doing these operations, right? So that's our answer in standard form, but let's put it together in scientific notation. I got the 6.5 times 10 to the 8th, and then plus 4.3, let's put scientific notation here, times 10 to the 5th. Now the idea here is you got to match the exponents together. It's similar to when you're adding fractions. You want a common denominator. similar but not the exact thing, but the concepts are the same, right? When you're adding or subtracting scientific notation, you need a common exponent on your powers of 10, right? So that's, I don't know if that helps or not. But anyway, if I'm going to take this 5 and move it up to that 8, that means I'm going to be adding 3 here. And if my exponents are going up, then my decimal is going to be shifting to the left. It's kind of the opposite of this situation here, right? So it's going to go 1, 2, 3. So we got a 0, and then the exponent right there. Okay. Now I'm going to add them together, right? 6.5 times 10 to the 8th plus, and again, I'm going to purposely make a mistake here. 0.0. Now you'll notice that I've lined my numbers up, but I haven't lined my decimals up. So this would also make a very odd answer that wouldn't make sense. So when you're doing your addition, right, just make sure that you're lining your stuff up. So it would be 0.0043 times 10 to the 8th. We would want...
We are in a secure. That means that nobody can come or go right now. If you are in an after-school club, you can report to the office, and we will call your families. Again, that we are in a secure, so nobody should be leaving or exiting our building. Thank you.
We're just going to add as we go down. So +3, +4, and then +5. And then we bring that 6 down. We don't change our exponents, so it's going to be 6.543 times 10 to the power of 8, which... it's the same thing. Oh, there is an extra 0 in here. Yeah. 4. Yeah, because we have 4 to the left. Yep, that's right. So there should be an extra 0 right there. Sorry. Okay, cool. So that's kind of like the idea, conceptually, why we do this shifting of our decimals left and right, and how we move our exponents up and down as we do one or the other. Okay, now let's actually talk about some like kind of real worldy situations here. We move on to our next one. So what is the distance between the Earth and Neptune at their furthest points, kind of as they orbit around the sun? One would be on one side of the sun, the other on the other. So this would be an addition problem, right? So we're going to take this 1.49 times 10 to the 8th, and we're going to add it to that 4.49 times 10 to the 9th. Okay, so let me write that down. 4.49 times 10 to the 9th plus 1.49 times 10 to the 8th. Okay. Okay. Now, I guess it's just a math teacher thing. I like, even though this was listed kind of on the right side of that drawing, I put it on the left side. I guess it doesn't really matter when you're doing addition or multiplication, but it does matter when you're doing subtraction or division. But anyway, okay. So again, we're going to match this exponent to that exponent. We're just going to add 1 here. Technically, we could bring this down. We could subtract 1 here, and as we move it down, our decimal point would move 1 to the right. Either way is going to get you the right answer. As we add 1 here, our decimal is going to move 1 to the left. So this is going to become 4.49 times 10 to the 8th, and then 0.149 times 10. Oh, this is to the 9th, my bad. To the 9th. Right? Yeah, good. Sorry. Okay, so now we're going to add, I'm just going to add an extra 0 here, and then add down. I get a 9, I get a 13, I carry a 1, I get 1 plus 4 is 5, plus 1 is 6. Bring down the decimal. And now, this is kilometers, right? Because we're doing like an actual word problem, you know? So what we would do, we would write out what is the distance between the Earth and Neptune at their furthest points. We'd say the distance between Earth and Neptune at their furthest points is 4.639 times 10 to the 9th kilometers. But I'm not going to worry about writing that sentence right there, even though you should know that since it is a word problem, you should write a sentence or paragraph summarizing it in your answer. Sometimes you will run into situations where your decimal point is not in the correct spot for being in scientific notation. Like sometimes it might be right here or it might be right here. And if that is the case, at the end of it, you just need to adjust so it's in scientific notation where the decimal point is in between those first two numbers, or there's only one number to the left of it. Basically, the number right here has to be between 1 and 10, but not including 10, right? So basically 1 through 9, right? So yeah, it can have numbers after the decimal, but just the number to the left has to be a single digit. Okay. Okay. Now we're going to do a subtraction problem. Okay. So we have our sun here. We have the Earth and Neptune, as they rotate or orbit around the sun at different speeds. At some point, they will line up-ish. Obviously, this image is not to scale. But what is the distance between Earth and Neptune at their closest points? So we have the distance here of 1.49 times 10 to the 8th, and then 4.49 times 10 to the 9th for Neptune. And the idea here is we're going to take this 4.49 times 10 to the 9th and subtract the distance of the Earth from the sun. So let me write that down. 4.49 times 10 to the 9th minus 1.49 times 10 to the 8th. If I were redoing this problem set, I would choose a different planet than Neptune for the second problem, because it's basically just going to be the exact same thing that we just did. But it's the same idea. We got to match our exponents up here, and as I add 1 here, I got to shift 1 to the left here. So this is going to give us 4.49 times 10 to the 9th minus 0.149 times 10 to the 9th. And then as we subtract, we got to add a 0 here. That's 10 if we borrow. So 10 minus 9 is 1. 8 minus 4 is 4. 4 minus 1 is 3. 4 minus 0 is 4. So this becomes 4.341 times 10 to the 9th kilometers. And again, since it is a word problem, a summary sentence would be something like, the distance between Earth and Neptune at their closest points is, 4.341 times 10 to the 9th kilometers. Okay, now we've got a multiplication problem. We have a space probe traveling at 2.5 times 10 to the 4th kilometers per second away from the Earth. I'm just writing this down as I go. Times 10 to the 4th. I'm going to put the units in here as well because I think it's valuable to see what happens when you actually include the units in your calculations. And then how far will it travel? And 3.15 times 10 to the 7th seconds. So how far will it travel? It's asking about the distance, right? And
attention, the emergency situation we experienced is now stable.
okay.
We can resume normal activities.
Okay, and the formula for distance is
Attention, the emergency situation we experienced is now stable. We can resume normal activities.
Formula for distance is rate times time. Good to God.
The emergency situation we experienced is now stable. We can resume normal activities.
Okay, rate times time. Rate is another word for speed, which you got right here, and time is just the number of seconds. So we just multiply them together. That's our last one. We'll get there in a second. Come on, Wishart. You literally had this up. Why did we do that? That's going to be right here. I got distracted by the secure perimeter. Times 3.15 times 10 to the 7th. And put the units in here as seconds. All right. So dealing with multiplication and division is actually way easier than addition or subtraction. So what's going to happen is you're going to take the A values, the numbers out front, and you're going to multiply them together. Okay? And then you're going to take your, let's see, can I do this in yellow? Will that actually show up? Your powers of 10, and you're going to multiply them together. 10 to the power of 4 plus 7. Now, you should already know about exponent properties that when you multiply exponential expressions with the same base, you are going to add your exponents. And real kind of tight in here, because I didn't leave a lot of room, we'll have kilometers per second, and then seconds. Actually, no, we'll put that at the end, because it's not, since we're kind of mixing things up, it's not appropriate to do that. Okay, but 2.5 times 3.14, this would be a time to use a calculator strategically. So it would be 2.5 times, if I can get it off the glare, 3.15, gives us 7.875. 875, and then we just add those together, so it becomes times 10 to the power of 11. Now, this is when I'm going to add my units back in here, because we have kilometers per second multiplied by seconds. Now, you should realize that this is a fraction, so it's a division problem, so it's a ratio, right? So seconds divided by seconds is canceled out, and you're left with kilometers, which we're looking for distance, so we're good to go, right? So your sentence defining this, or answering this, would be, how far will it travel in 1 year? It will travel 7.875 times 10 to the power of 11 kilometers in 1 year. All right, last one. This is going to be a division problem. It's the same exact graphic that I had for the subtraction one. However, we're asking how many times more than the distance of the Earth from Neptune. The distance from Neptune, the distance of Neptune from the Sun is how many times more than the distance of the Earth from Neptune. You might think this is a multiplication problem because it says how many times, but it's actually how many times more, so it's a division problem, okay? Like if somebody had a summer job where they made 10 grand and somebody had another summer job where they made 5 grand, right? Person A made 10,000, person B made 5,000. Basically, how many times more money did they make? It would be 10,000 divided by 5,000. They made 2 times more, right? So that's kind of like the thinking that goes along with this. So let me write los números down here. Kilometers times 1.49 times 10 to the 8th. And there you go. Okay. So just like multiplication, we don't need to worry about shifting our decimals or matching our exponents. We can just do the division. This should be division, not multiplication. So we're going to take our numbers out front, our a values, and we're going to say 4.49 divided by 1.49 times 10 to the power of 9 minus 8, right? When we're dividing exponential expressions with the same base, you subtract your exponents. So then we do that 4.49 divided by 1.49. 1.49 divided by 1.49 gives us 3.01. We will actually just round that to 3, okay? So we end up with 3 times 10 to the power of 9 minus 8 is 1. This would be times more, right? And you would be like, the distance from Neptune to the Sun is 30 times more than the distance from Earth to the Sun. However, we can actually, I don't know, commonsensically think about why we use scientific notation in situations like this. We use scientific notation when we have very, very big numbers, right? However, this number is just 3 times 10 to the power of 3 times 10 to the power of 1, which is the same thing as 3 times 10, which is 30, which is not a very big number. So I would argue that in your response to this, your sentence would be like, rather than saying 3 times 10 to the power of 1, you would say 30 times more. And that's that.